AP Cammers, and here we are back to idea part 4. And so in this one we want to look at the process of following energy throughout reactions. Of course, anytime a reaction occurs, energy is going to go one of two ways. Energy is either going to need to go into the situation or it's going to come out of it. And so basically it sort of works like this. It's all about forming bonds, okay? And everything, of course, relates back to Coulomb's law and forming bonds and the whole interaction of electrons. But basically, when a bond is formed, so if a bond is formed, then what happens is energy is given off. So anytime you form bonds, anytime you bring atoms together in new forms, energy is given off. Energy given off, all right? So think of energy going away. And anytime bonds are broken, energy is absorbed. So basically, it takes energy to break apart bonds, and then forming bonds typically are. So what happens is it releases energy because what's happened is that these things have come to a different energy state, and the whole point of bonds is so that you can have a lower state of energy or sharing of electrons. So everything wants to seek to in lower energized state. So let's say bonds broken. Okay, so then energy is absorbed. And another way to say this, which is often what we use in chemistry, is the idea of exothermic and endothermic. So this one would be like what we call exothermic, and then below here would be what we call endothermic. Okay, now very important for you to always analyze what's going on in any chemical reaction of bonds formed versus bonds broken. So what we call this is a change in enthalpy. So enthalpy is basically the measure of any energy that's either released or absorbed by any substance when bonds are broken or formed in a reaction. So that's the best definition of enthalpy. It's the energy or the measure of that energy that is released or absorbed as a result of bonds forming and breaking in a chemical reaction. Okay, so the formula goes like this. H is the enthalpy, we use H, so enthalpy, and I just defined it as the energy measured from breaking and forming bonds, equals the enthalpy of the products minus the enthalpy of the reactants. So all you have to know is the enthalpy of what's going in and the enthalpy of what's coming out, and you just have to subtract them. So basically, all substances like to be in the lowest possible energy state, and because that gives them the greatest stability. And so that means basically exothermic processes are most likely to occur, because an exothermic process means that we've gone from, so when you're going to an exothermic process, you go from a higher energy state to a lower, right? And the lower the energy state, the lower the amount of energy they need to stay together, the more stable it is, right? So if I go from a high to a low, well, how do I get from a high to a low? Well, I have to give off some energy. So energy has to be released to go from a high to a low. And so this is what we call exothermic. So essentially, what's going to happen is that exothermic processes are going to occur on their own, and we call that spontaneous. So the idea of spontaneity is going to come up a lot. So spontaneity. And so spontaneity is the idea of things going from a high energy state to a low energy state. So now let's look real quick at a couple of examples here. This example was on the AP exam, last year's AP exam, the 2013 exam. And what it asked you to do was to draw an energy diagram, or to illustrate the energy changes that occurred in this reaction. And so they gave you two steps in the reaction. They gave you step one right here. You see this combining with this gives you this intermediate right here, and then the chloride And so, so there's the intermediate used right there, and then to get us to our final product right here. So this is the rate determining step. So a rate determining step is the one essentially that takes the most energy. It's the one that that basically is going to be the bump to get over. And once you're past that, then everything can flow. Now, of course, this hinders everything or slows everything to its speed, whatever it is. So, so then this is a fast step. So then there's a step 2 in this reaction right here. So most reactions don't just go from one thing to the next, right? Because the overall reaction in this one would be, if I was to write it, it would be this plus this goes to this, right? But in between there, we have, you know, these different things created. We have these intermediates created. We see the chloride ion is an intermediate created in the C2H5+. So both of these intermediates are created in the process of this. So how do we show this? Well, we are told that this is an exothermic process. So if it's an exothermic process, we know this is potential energy. We know we're going from a high energy state down to a lower energy state, right? So this is our potential energy. So the progress of the reaction, we know for sure, is going to start somewhere high and end up somewhere low. Now, we don't really have numbers over here, and there wasn't numbers given in this AP exam question. So all you really have to do is illustrate that it goes from a high to a low. So this rate determining step is going to take a certain amount of energy, and so that's going to create a bump, okay? And then as we go down, we have this second step right here, which doesn't use as much energy as the first one, but it uses some. And it's going to be a bump in the reaction because this has to occur, right? But it's a very fast step, so it's a small little thing that basically occurs along the way. So you end up with 2 bumps representing these 2 steps in the reaction, okay? And then this right here, this bump, to get over this bump right here, is what we would actually call activation energy. So every single reaction has a certain amount of energy you have to put in to get it to go. And we call that activation energy. It's also the rate determining step, but it's what we determine our kinetics and our reaction order from. And so anyway, so here's a typical exothermic, and if all you had to do on the AP exam was to label the activation energy and draw a diagram that showed these steps as an exothermic process. So let me give you a couple more examples. Here's the exothermic and endothermic energy diagram. So endothermic is exactly opposite of that. So here's our potential energy. When we're in endothermic, right, we're going to go from, let me turn on that layer. We're going to go from a low energy state, right? So here we are down here at low energy to a higher energy state. So in order for me to go from a low to a high, I have to input energy, right? So my activation energy is going to be this huge amount right here because it takes an input of energy to get from here to here. So, so here's my change in H. Of course, my change in H is the difference between the enthalpy of the products and the enthalpy of the reactants. And my activated complex, and when we say activated complex, we're looking at the highest energy state within the reaction. And there's always a point, which is the top of that activation energy, like I showed you in this one right here. There's always a high point where it has to get to that high point to go. It's sort of like this is the highest energy. As soon as you aggravate everything to this highest energy state, the rest of them go off. And so that's the activated complex. So it's essentially the assortment of these molecules banging into each other, which have the highest energy state of all. And this is always a state of energy that's higher than anything. It's always the highest of the reactants, products, anything, and it only is happening during the reaction itself. All right, so then if we look over here at exothermic, just like that one we drew, so we're going to go from a high energy state to a low energy state. So we're going to give off energy to get there because we have to reduce the amount of energy as we're going from this to this. Now, this would occur on its own, because I told you that everything wants to go from a high energy state to a low energy state. Everything wants to be at a lower energy state. So this one is going to require some kind of process that makes this happen, or it's either going to be driven by a high amount of entropy. We'll get into that later. But here, once again, here's your activation energy. Activated complex is the highest energy state. So we get over that, and we can go all the way down. So this is exothermic, showing you the energy diagram of an exothermic reaction. And then there's one other sort of energy diagram that's going to, and then also one other point that I need to, when you draw a line, so here's where the reactants started, and here's where the products ended up, right? Remember, the change in enthalpy is the difference between the enthalpy of the products and the enthalpy of the reactants. So on this diagram, this here represents the enthalpy change, okay? So, and then this here, this extra bump of energy, that's just the activation energy. That's just the energy needed to get it started. That's like the match needing to light the paper, and the rest of the paper burns on its own. All right, so let's go to one more thing here. So oftentimes in like biological systems, we have catalysts. Now catalysts, basically all a catalyst does is something that goes into the reaction. It's not changed in the reaction, so it can continue to be used over and over again. But what it does is it speeds up the reaction by allowing the reaction to go with less activation energy. So if here's the energy needed to get this thing going without the catalyst, you see, to get to this activated complex, we have to go way up here. But you add the catalyst in. So essentially what a catalyst does is it'll grab onto these molecules in such a way that it gets them to their activated complex quicker with a lower amount of energy, okay? And so then once it gets to its activated complex, shoo, it can go, and it can get down to its products right here. So this is how a catalyst speeds up reactions. So you can notice the only difference between the catalyzed reaction and the uncatalyzed reaction is that the energy of the activated complex is lower for the catalyzed reaction. And so all it really does is change the activation energy. The change in H is the same, right? So with or without the catalyst, there's no difference in the change of H, because the change of H is measured as the enthalpy change between the reactants and the products. And all the catalyst does is change this initial bump to get over it. So that hopefully that helps to understand catalysts. And so our body uses catalysts a lot of times in order to make a reaction happen. And then when there's no catalyst, of course, this stops it. But as soon as you put the catalyst in, the reaction can go. And so that's how our body speeds up and slows down reactions. So in the next videos, we're going to go into a lot more detail about enthalpy, entropy, oxidation, reduction states, and electrochemistry. Stay tuned.